Welcome back to Corey Ross's Schools. We're going to try to do Bernoulli's principle today, which I don't think very many people understand it. Even among former students, I probably couldn't name 10 students that I've had in decades that really understood it. So this is something students struggle with. I really have a hunch that most of the teachers out there that are trying to teach it are doing, I can't remember what they call that, but they're faking their way through it. But the idea is if you've got something moving fast, a fluid, now when it constricts down, it has to speed up because mass has to be conserved. So all of these molecules have to get through there. They have to go faster to get through there. And then they speed up. What happens is something very surprising. The pressure, you would think, using intuition, it would have to go up, but it goes down. It just does. And it's the explaining why part that people have trouble with. So let me give you an explanation that hopefully makes sense to you. That's a little bit theoretical, but without using math. Oh, by the way, some years ago, I made a flat piece of cardboard cutout, and I trimmed the edges on the back. I sliced the edges so they could tilt them forward, and they would move around on this without getting away. And I just took a Bic pen and sliced it open and hot glued it onto another piece of cardboard that fits in there. And as I blow the air out through this pen really fast, it hits this cardboard, and then it only can go this way, this way, this way, this way, this way. So it has to go in this kind of plane here. And it goes out fast enough that this plane can't get away from that one due to the Bernoulli effect, and it gets stuck. So you could make one of these, and it works. All right, so there's my demonstrator. But let me give you an explanation. Let's say you have a tube, and it's as the tube's been sitting in the room. So how does the temperature outside the tube and inside the tube compare? And students might have different opinions about this, but if they think it's colder in here and some will think it's warmer in here, and you challenge them to explain why when it's all the same temperature. That means that the kinetic energies of the particles in here has to equal the kinetic energy of the particles out here on average. And kinetic energy is 1/2 mv squared, 1/2 mv squared. And since a milliliter of that air out here and a milliliter of the air in here have the same mass, and they both are divided by a 2, that on average, the speeds of these particles and these particles have to be the same. You've got to be able to explain why if they're not at all times. So if you get this air in here moving fast this way, it can't have more overall motion than the air particles out here. So this explanation is theoretical. I'll leave you to think about it, prove it, or whatever. But I'm going to assert this. That if these particles are busy moving this way as opposed to every which way, they can't have more motion. So they must have less motion in other ways, like to the sides. They would have to. Just mathematically, it has to work out. And that is an explanation for what causes the sideways pressure in here to be less than out here if the fluid is moving fast through here.